doing back and forwards and just making sure that we're on the same page, because you're not crazy. This is really hard.
Okay.
And it's important. And so the combination of being hard and important means we should spend some time on it. Okay, so, oh, good. So do you care which one, Megan, or?
Can we do B?
Yeah, because it's going to be longer. Okay. You can see my screen. Perfect. Okay. I was teaching my graduate class, and they're not very communicative. And so I went on for about 10 minutes drawing stuff before somebody asked, are you drawing something? So I wasn't sharing my screen. Okay, so we have this, right? Chromic acid, water, so chromic oxide, chromium 6 oxide, water, acid. So if we draw out the chromium, it's that. How do we know that that's the structure? Well, there's no charge on the damn thing, and the oxygens need to make 2 bonds. Metals, you know, can adjust their oxidation state depending on what's needed, right? Depending on what it is. So this is chromium 6. So mechanistically, what we're going to be doing is, I just looked at the list of this thing, but one thing at a time, Trent. Okay, we have strong acid because we have sulfuric acid. Interrupt me at any point, Megan, okay? Let me know if I lose you when I lose you. So the carbonyls are definitely the most basic thing present. That's because carbonyls are basic at the best of times. Now that they're attached to a chromium, they're much more basic because chromium is a metal, and so that oxygen-chromium bond is going to be really polarized towards the oxygen. That's unstable. So I can technically, this will probably form with water first. Probably should do this the right way. And if we think about sulfuric acid structure, you know, H2SO4, just up here in brackets. Things that have lots of oxygens attached tend to like this form of 2 oxygen double bonds and 2 oxygen single bonds. Okay. Now, this is our reagent. So sometimes you'll actually see people write this thing as the reagent, but you actually can't buy chromic acid. You have to make it. It's a mixture. But this is what the reagent is. This is what's going to do the chemistry. And here I'd accept a lot of different things. So the way I did it in class is I transferred this proton from this OH2 to one of the carbonyls because the carbonyl is more basic. It's just we're transferring from a more acidic site to a more basic site, so it's favorable. How are we doing so far?
Wait, sorry, could you repeat that last part?
So, perfect. So here we have a positively charged oxygen, but it's like an alcohol ether oxygen, right? Single bonded. Whereas here we have a double bonded oxygen that's positively charged, and that's always better. Carbonyl oxygens are always more basic. So the carbonyl of a ketone or an aldehyde, or the carbonyl of an ester or carboxylic acid is always the more basic site of those systems.
Okay, got it.
And it's because you can draw a resonance structure with an O- and a Cr+, so there's more electron density on the oxygen. when it's when it's attached to a double bond. Whereas with the single bond, it doesn't have that option. Does that help? Like we can kind of delocalize the charge a bit by resonance. Okay. So now what we're going to do is we're going to use our alcohol. I'm going to try and keep the alcohol in a different color as we go so we can keep track of who's who.
Wait, sorry, so the last structure you drew in red, would that be our reagent?
Yeah, like yes, like these are both because they're past equilibrium, right? So they're both the reagent. Yes.
Okay.
This is probably the. It's in equilibrium, so they're kind of very much like they're flipping back and forth. So that's probably the active one. Let's write that. Okay, so if we follow through the arrows I just drew there. We have that. So at this point, chromium doesn't want to be making have this many oxygens. We still only have 6 bonds to oxygen. We're still chromium 6, but now we're attached to, it really likes doing this, like having those 2 double bonds and 2 single bonds. Why? Because it's using its d orbitals, and that's the preferred geometry. It's the same reason sulfuric acid does this. Do I want to really talk about why that's the geometry? No, and it's partially because I don't know. I think I knew this in the past and it wasn't relevant, and so I forgot it. So I'm sorry. I think I am saying that is the more stable form for these kinds of things because I am telling you so, and that makes me uncomfortable. I'm now going to do a transfer of the proton because at this point, it can easily go back to what it was. Now we want to kind of stabilize this. So I'm transferring that proton around, and I'm going to put it on one of the other waters. Why am I doing that? Because if I do that, the reaction can move forward. If I don't do that, we just go back to where we were and we just kind of shuttle back and forwards. Like this is in equilibrium with that. Like this go back and forwards. The alcohol can come in, the alcohol can go off. Alcohol come in, alcohol go off. In, off, in, off. When it transfers the proton, something new can happen. Sorry, stick with my colors. Which is very favorable because now we're going back to.
Would it have mattered which one we transferred?
No, not at all. They're all the same. You could even transfer it to the carbonyl and you could draw something reasonable that would have worked just fine as well. You would have taken a step or two, but you would have gotten here anyways. So we're back to making chromium with 6 bonds to oxygen with 2 carbonyls and 2 alcohols. It's just we swapped out a water for alcohol. That's right. So now this is where the E2 thing comes in. And notice that, you know, this is impossible to do at any of the other oxygens because none of the other oxygens are attached to a carbon or attached to something with a hydrogen, but this one is. And so now we can use one of the waters that we've liberated. Sorry, I drop that. And we can do this E2 reaction. Okay, this I completely admit is kind of complicated. So what we're doing is we have a leaving group on the oxygen, and it's chromium itself is the leaving group. So we haven't done this kind of thing where electrons go onto an atom and it breaks a bond, because we've been working with normal atoms like second row elements, but chromium's a metal, and so it's 6+ right now. Like it's formally 6+. It's chromium 6. That's a very high oxidation state. And so it can accept 2 electrons and come down to chromium 4. Now, carbon's not doing that. Oxygen's not doing that. You know, you break a bond to oxygen, you form a new bond to oxygen. You don't sort of just store extra electrons in oxygen and don't have to pay any price. Metals are weird. So we move 2 electrons onto chromium, but then we need to release 2 electrons because it only has so many orbitals, and the one we release is one of the double bonds to the oxygen. So when we do that, if we note what we get is we get an aldehyde. And if we check, we don't need to worry about the other reagent. It'd be perfectly full marks if you just drew that and didn't worry about what else was going on, because we don't care about what else is going on. But you've got this guy, and now we count the charge on this, and this is shifted to being chromium 4 from chromium 6. And where those 2 electrons came from was that chromium oxygen bond. So we've oxidized the carbon, and we've reduced the chromium. So this is overall as an oxidation of the alcohol to an aldehyde. Now, since we're under acidic conditions and we have water, if we go back to the carbonyl lectures, we know that all aldehydes under acid and water you can protonate them. But it mostly lies towards starting material because there's so much water. And then you can add the hydrate. Add another water to this. It's a nucleophile. This is just carbonyl chemistry. The nucleophile is water instead of cyanide or something, or methyl lithium or whatever the case may be. Normally, we don't think too hard about this because it's not productive. You make your silly hydrate. But it's back in equilibrium with the ketone. And sorry, I don't know where this extra carbon came from. And normally, this is the ketone. This is the hydrate. Much more stable. At any one time, actually, if you look at any ketone, it's about 99.8 to 0.2 is the ratio. But these are, if you have a ketone in water, it is in equilibrium between the ketone and the hydrate, because of course it is. There's no reason it can't do this. It's just the ketone is much, much more stable. So almost all of it is the ketone. So normally this is completely irrelevant. It doesn't matter at all. We don't even think about it. We just say, hey, we got a ketone. But if there's a really strong electrophile present, the hydrate can act as a nucleophile. Like a ketone is not nucleophile. Like carbonyls, oxygen double bonded, that's not nucleophilic at all. It's basic, but it's not nucleophilic. Alcohols are nucleophilic. And if you have a really strong electrophile, the alcohol can react. And now you have 2 alcohols. And the Jones reagent's a really strong electrophile. So if we go back and we react this with some more Jones reagent that we made, I'm not going to show making this one again. Nothing is stopping us. The little bit that is made of this, the little 0.2%, when it's made, it reacts. Then it's consumed. Then more ketone gets pulled over to the hydrate. It gets reacted. Then more ketone is pulled, and eventually all your ketone has been pulled over to the hydrate, and all of it's reacted. So what we're doing is we're basically removing one side of the equilibrium and driving the equilibrium forward because we're removing one product of the equilibrium. And when we do that, just keeping track of where everything's coming from. This is it's identical to what we saw earlier. Like it's the same case. Again, we're going to do another proton transfer, the same one we just did. Well, not just, but like, a couple minutes ago. And as you were pointing out, I just arbitrarily picked a an oxygen. I could have picked any of them. So at this point now, I'm running out of colors. We're in that same E2 situation all over again. We've got a leaving group. The leaving group is the chromium and the water that is on the chromium. So we're going to grab that hydrogen. It's going to make a new oxygen carbon double bond. We're going to break the oxygen chromium bond, and we're going to lose the water. And again, since 2 electrons are coming onto chromium, it needs to break a bond because it needs to use that orbital. And so it breaks the OH2, one of the water bonds. And what it does with that, the water drifts off. And we're again taking chromium from chromium 6 to chromium 4. We're creating a new oxygen carbon double bond, and we're removing this hydrogen. And if we follow through what we get there, so we regenerate our acid, which we start with the sulfuric acid as a catalyst, right? We constantly, we start with some acid, we have the acid at the end, the sulfuric acid was catalytic. We have made the chromium 4, and we've made a carboxylic acid. And the original double bond to make the carbonyl came from the first oxidation. The second one, the second oxygen came in because you made a hydrate from the aldehyde, in this case. And then when you had that aldehyde, the hydrate could react with another equivalent of the Jones reagent. There was another hydrogen to collect, so it could do that elimination. If this was a ketone, if there was no hydrogen there because there was another carbon, we could get all the way to this step. but then nothing more could happen because there would be no hydrogen there. And so it would go all the way back. And we would just lose the chromium. And you'd exchange your alcohol for another water, and it would actually flip all the way back to the ketone. Everything here, even this one here, I should have drawn that, is in equilibrium. Everything's in equilibrium until this final step where we do this E2 elimination. So if this is a ketone instead of an aldehyde, it can't go any further. If it's an aldehyde, that proton is there to be removed to make the acid. Did that help, Megan?
Yeah, I see what you did. I'm just confused on how did you know you had to go past the ketone? Like I probably would have just stopped there.
Right. So I think it's the idea that I think it's so it's not a stupid question at all. And I'm trying to think how best to answer that. Okay, I guess I have two answers for you. The first one is it is not obvious. I think the reason we know so I think the first person who probably would have drawn this mechanism, and I'm retconning history a bit here because they would have done this chemistry before they would have drawn mechanisms like this. But the first person to draw this mechanism would have stopped at the aldehyde too. But what happens is when you take an alcohol, a primary alcohol, and you treat it with the Jones reaction, you don't get an aldehyde, you get an acid. So we know you get an acid. And so then it's like, well, shit, how do I justify this? Like a lot of mechanisms are trying to justify what happens and explain something reasonably why it could happen. In this course, it's a little tricky because I'm almost sort of saying, hey, this reagent does this mechanism. And it's not always true. But for this course, we're trying to keep things reasonably simple because we're still building some very basic building blocks. So I think I know to go past the aldehyde because the reaction goes past the aldehyde. The reaction gives me an acid. And so it must. And it's like, how can I justify that? How does that work? Because the aldehyde can't do it. The aldehyde is not a nucleophile. But look, if I have water present, I can make the hydrate. Now the hydrate's a nucleophile, and now it can do the same thing. The reason this matters is the other set of conditions I have right below that. C is using PCC and DCM, and I went through that again in the. I go through the mechanism for that in the class, and the PCC is very, very similar, and it's also in but it's not. It doesn't have any water, and so it stops at the aldehyde because there's no water to do this whole thing here. So it does the first one, it reacts the alcohol to the aldehyde, but then it stops because there's no water to make the hydrate. And so the PCC stops at the aldehyde because there's no water. The Jones reagent goes on to the acid because there is water. What water does is it makes the hydrate from the aldehyde. Does that help?
So with the Jones reagent, we'll always get like the acid at the end?
If it's a primary alcohol, yes. If it's a secondary alcohol, no, because there's no proton to make the acid. Like to make an acid, you need to have the carbon needs to be at the end of a chain. The carbon's in the middle of a carbon chain, you can't make an acid, right?
Oh, okay, I see, yeah.
So yes, the Jones reagent will always give you the acid on a primary alcohol, so an alcohol at the end of a chain. On an alcohol in the middle of the chain, like a secondary alcohol, it'll give you always a ketone because it can't go further than a ketone because there's no proton. And on a tertiary alcohol, it won't react because there's no hydrogen for it to eliminate. Like you need that hydrogen.
Okay. Thank you so much.
Okay, cool.
Dr. Tran, I have a quick question about the PCC. I was trying to find the mechanism in the YouTube videos, but I couldn't. Are we responsible for knowing the mechanism?
You know what? If you've looked and I didn't put it in there, then no, you're not. You're responsible for knowing the reagent, but not the mechanism.
Okay.
You can look it up really easily on Wikipedia, I think.
Mm-hmm.
But if I didn't put it on there, then I will not ask the mechanism of PCC on the course.
Okay.
Yeah, I'm just looking it up online. Yeah, it's real easy to find on. That was like 2 seconds of Googling. So yeah.
Yeah, but we can't
But-
Google.
Well, you can. Like you just can't. You can't Google Chegg, but you can definitely use other resources.
Okay.
Yeah.
I think Alyssa had a like she was here
Yeah.
before me.
Alyssa
so.
posted some questions, so she really just So Alyssa, do you want to tell me what your question is? I think I know, but
Yeah, sure. Okay, so for the first one, I just got confused. It's a substitution reaction, and I got confused because of the like the reagent. Like that.
you know what? You're almost there. You just made a mistake. I don't see your full answer.
I can show you the full answer.
Right, but I can sketch out what I have from you.
Okay.
And then let's see if you can see where you went wrong. You're not wrong strategically, and you're going to go seriously. The response, I believe.
I swear, I tried to like submit it about 15 times, and it just wasn't working.
Okay, so what you drew, as I think what I see your answer is that.
Yeah, I think so.
Okay. So, what kind of reaction is this? You're right strategically. So tell me what you think, and then we'll walk through and sort of figure out where you went wrong. What kind of reaction is this?
I thought at first, oh, can you hear me?
Yeah.
Okay, so I thought at first you would make the H or the OH attack the H and then have water as a leaving group.
No, you use H as a nucleophile.
Right.
As a base, sorry. The H, sodium hydride, the H is basic.
Okay.
So you do an acid-base reaction. So you have O minus as there.
Okay. And then for the second, or for the solvent or whatever, so we have Br as the leaving group, and then you have the alpha carbon or whatever those are called right next to it. So the O would attack that carbon.
Okay. So is that what you've drawn as the product? I agree. You are 100% right.
Yeah. Yeah, I think that's what I drew as the product.
Is that the product? Here's what you drew as the product. Is that the product of the arrows that I just drew?
Like, is there an extra methyl or something?
Yep.
See, I think I drew. Sorry, one sec. Just trying to find the questions again.
So you did everything right.
Okay, so I just forgot.
The question of water is a leading group thing. I'm going to pretend that you meant to say you're using it as a base. But
I'm getting conflicting things from the textbook and from what you're doing, because they do say that water can be a leaving group, and it can, right?
Oh, water absolutely can be a leaving group. If you protonate it, if you add an H plus to it, you get OH2 plus. That is a leaving group, but this is basic conditions. This is an acid. Okay. Yeah, no, absolutely, water can be a leaving group.
Okay, yeah, that makes sense. H plus, yeah.
Yeah, this is H minus.
Okay, that makes a lot more sense. I just forgot the methyl.
Cool. Yeah, you forgot a methyl. Okay, your next question.
So second one,
I did that really well. If you ever start getting confused about something, just start numbering your atoms, and just make sure it's like, okay, now atom A and atom 6 need to make a link, and just make sure that that's a product. If you're ever thinking you're getting a bit confused. Okay. Draw the major product for the following reaction. Yeah.
Yeah, I had asked you the question about the rings. I'm having an issue like trying to see where they fit together. And so I'm trying to number them, but I don't know, it's just not a great strategy for me. I need a different strategy.
Not intuitive for you. Okay.
So
I don't even know. Maybe actually, I'm using these colored pens.
tried
so maybe
putting
even-
the sorry, I can't.
Sorry.
The SET. Can you hear me?
Yeah.
So I tried putting it. My quality. It says bad quality. I'm not sure if you can still hear me.
I can hear you. Yeah.
Okay. So I was confused because I tried to put the double bond right next to that methyl, like to the on the bottom carbon to the methyl.
I can't see.
And then I also
answer.
tried.
Yeah.
So yeah, I just thought that you would attack the carbon where the bromine is at.
Mm-hmm.
And since there's resonance next to it, I thought that's where the double bond would be.
So like you thought double bond would be. I actually think I can see two answers to this question. So you thought the answer was that?
I thought it was either that or I think it's a 7-membered ring.
It is, yeah.
Okay, is there another? Well, it can't be right next to the other double bond. That doesn't make sense.
Well, this is the proton to remove to do that as an E2. So if you're doing an E2, it has to take off that hydrogen. There is one other mechanism it can do. This is so this is the mechanism I would expect you to answer for this question. So if I ask this question on an exam, this would be my expected answer. It's because
see, that's what
this is a good nucleophile, but you have an excellent elimination because the double bond is going to be in conjugation, and eliminations take over at that point because conjugation is amazing. And so if you can make a double bond in conjugation, that's awesome. So even though an SN2 is possible, I think that's more likely under the rules that we are using. However, they might have a different product.
Okay.
And the product,
I think
they might have drawn the SN2 prime.
All right, they're saying it's incorrect.
Sorry?
I think that they're saying that your answer right there, like with where you put the double bond, I think they're saying that that is incorrect.
Incorrect. Right. So the other answer I've got, and this is not what I would ask in this course because we haven't covered this, is doing a reaction called an SN2 double prime. What the fuck does that mean? It means that I'm doing kind of an SN2, but I'm now spacing it away by using double bonds. And I'm attacking the far end of this entire system. So if I follow those arrows through, it might be taking that as the product.
I see.
And I'm attacking this carbon, and it displaces this double bond to here, which displaces this double bond to here, which kicks off the leaving group.
So, the SET, that's kind of stick-like, so why wouldn't it have been on the methyl? Or like, why wouldn't it have...
Directly here? Like, why doesn't it attack the carbon with the bromine on it?
Yeah.
You know what? I wouldn't ask this question because it's a borderline question to me. I think that's also possible.
Okay.
What I'm going to say is SN2 double primes like this tend to be more favored over SN2 primes because if we think about the sterics of this, so electronically, they're actually very similar. Like it looks like I'm pushing a lot of arrows, and you're like, how is that good? Resonance doesn't care, right? Resonance doesn't care how far things are. It's resonance. The electrons are all flowing. And if I consider this carbon here versus this carbon here, this guy here is less hindered. This guy's got a bromine, it's got a methyl group near it, it's got more hindering. This guy here is completely unhindered. So if I'm a nucleophile, this guy here is more approachable.
So
it's also more approachable because it's an sp2 center, and all sp2 atoms are always less hindered than sp3s.
I see.
So
okay.
these are favored. We have not covered this in class. I am not going to ask you any questions that involve distal SN2 displacements. Like, this course already has way too much material in it. The last thing we need to do is add a whole bunch more.
Fair enough.
Yeah, that's fine. There's all sorts of things that I could have covered and I chose not to because it's just too much. And there are kind of edge cases like this where it's like, yes, it matters. Yes, you might have to learn it later if you do more of these courses, but for now, the basics are what's really important.
So I just wanted to clarify the product that you drew in green. That one would be the like Zaitsev elimination product,
yeah, absolutely.
Right?
Yeah, it would also be the hot. There is no other elimination possible.
Okay.
Can I ask a question about this one too?
Yeah.
So I was just trying to like mentally like do it and see which one I would choose out of the 4 mechanisms. So I know that SN1 and E1 are not possible because of the basic conditions. So when we get to then SN2 and E2, I thought because the nucleophile is stick-like, then that would favor the SN2.
I think so. If I did ask a question like this on an exam, it would probably, as I said in class, I might ask a question which is a borderline case. And I would say, comment on the reactions, explain, justify your choice.
Oh, okay.
And so this, I'm right now, I have drawn both the red and the green product. I'm going to tell you that one of these is the major product. I don't know which. I would actually have to run this reaction. I can't tell you if this is an E2 or an SN2. My bias is to be thinking that it's going to be E2. I expect if I did this reaction at room temperature, I would expect to get the E2 product. But I would probably also get some SN2 double prime products like the one I got in red. And I think your logic thinking, hey, your logic saying, I think this is stick-like. I got a secondary leaving group. It's a good leaving group. I'm going to go with the SN2 for that. As long as you also consider that the E2 is possible, which you've said, I think you're looking at full marks for the question.
See, I'm confused now because the chapter is substitutions.
So they're probably doing this.
Okay.
I assume you tried directly displacing the bromide, but that's actually not.
I did.
Yeah, that's not going to be preferred. It is going to prefer this SN2 double prime. And if that's not the right answer, the textbook is wrong. And if, you know what, if I look at somebody's textbook answer grade and they're like at 98%, I'm rounding to 100 because like they completed almost all of them and 1 or 2 are wrong because the textbook has got some errors. I'm not worrying about that.
Okay, thank you.
Yeah, the textbook is meant to be free grades. I'm just looking like, hey, this student didn't do the questions. They don't get marks for it. This student did the questions. They get marks for it. I gave some percentage for it to be correct because otherwise there'll be no penalty for somebody on the last day before the exam just quickly going through and typing A into every box and getting full grade, which isn't quite the point. So it's trying to balance. I don't know. I have no idea how to. I have no idea how to encourage people to keep up with the material. You guys are not my audience because you are keeping up with the material.
On another note, I have one more question.
Yeah.
For the alkene assignment,
Yeah.
for 2C, I'm just wondering about the product. Like,
Sorry, I left again by accident because I pressed the left button instead of a dismiss button. Sorry, what were you saying?
So I'm wondering about 2C on the alkene assignment.
This is my assignment.
Yes.
What's the assignment number? 3?
Yeah, 2. I think it's 2.
Let me pull it up. Teaching assignments. Assignment 2. 2C.
Yeah.
Okay, so it says
It's the
that one, right?
MCPBA one. Yeah, yeah.
Okay, so this is covered in the lectures, I know.
Yeah,
Okay.
I just was wondering, like, you get to a point where you have like your 3-membered ring to OH.
Yeah.
And then like once you kind of but move one of those bonds to like to bring in the water. I'm just wondering, like, would it be incorrect if I mixed them up? Like, I mixed up the one going into the page and the one going out of the page.
No,
would it be?
it's okay, because at this point, it's arbitrary which way I drew that epoxide, right?
Okay.
I should have been, I think I don't love my answer for that, or my question. I think what I should have drawn instead is, so I know this looks very much like the same thing, but what I'm saying here is I'm not saying this is down, that one is up. I am saying they are opposite each other. So it's full marks if you have them opposite each other, but you have them the other way around.
Okay, yeah, because I was just wondering if there was some sort of like technique that I needed to use to make sure that they're on the right side.
You actually can, but that's not what I'm asking. Yeah, that's asymmetric synthesis, and that's like, you know, we have fancy ass ways of doing it, basically to get one enantiomer. But no, that's an error on my. That's my question being a little bit unclear. I meant them to be opposite, but you don't necessarily need them.
Okay.
It can either be, as long as they're opposite, and you can open that. That also gives you an option. You can open that epoxide using either acid or base. And
Right.
you have opposite. It doesn't matter because you'll attack different carbons if you use acid or base, but they'll be opposite either way. And
in this situation, it would have to be like water or OH, right?
Yeah, you'd have to use water or hydroxide, right? Because if you use an alcohol, you would have an alcohol.
Right. Okay.
Yeah.
Sorry, I just had one last question. I lost it. One sec. Okay, I completely forgot it. I will get back to you in like a minute or two. Once someone else asks the question. Sorry.
Simon 2 questions 1. So that was Guntas. Oh, Simon 2 question 1C. Yeah, no problem. I think that might be one of the ones I made a correction to in the answer key. So this again is Markovnikov addition of water without strong acid. So we attack the Hg. I should have added OH. There's no water. There should be water in that mechanism. It is impossible without water. That question, no one's ever pointed that out to me. Just everyone's kind of gone, yeah, because they draw water in the product and there's always water. Yeah, definitely Melitza. Okay, there's water. I'm sorry if that was the confusing thing, the lack of water, then you're absolutely right. No one has ever pointed that out to me. I'm just looking at this now going, shit. Alyssa, I could definitely ask those because they apply, but I'm not going to actually. Okay, I'll get back to Alyssa. I'll get back to Guntas and I'll come back to your question, Alyssa, because it's a good one. So what we need to decide is, do I want the positive charge there and a mercury acetate here. Realizing that makes a 3-membered ring, but we're thinking about sort of where the most of the positive charge is, so where the water is going to attack. Or do I want positive charge there?
So I thought it was the first one because you can do resonance with oxygen.
Well, what I can do is I can do that, right?
Yeah. Mm-hmm.
Okay. I agree there's a resonance structure. I want us to think hard about whether that's a good resonance structure.
Well, the octet is full, so isn't
Is
that
the octet
good?
full?
Yeah. No.
You sure?
No, it's not. Oh, okay. Oh, okay, that's what was confusing me.
So it's a bad resonance structure, but still, resonance is still good. So you're
Mhm.
not stupid. You're not. You're thinking about that right. But what else do we have to consider but the resonance is not good. It's not great. It's still better than no resonance. Even bad resonance is still better than no resonance.
Mhm.
Still delocalizing. So on its own, if that was the only factor present was resonance, you would still be
Induction?
right. Induction, right. Because what's happening with the induction, right, is
Yeah. Mm-hmm.
we have this pulling out, and we also can actually draw a resonance structure, a pretty decent one. Well, no, it's not decent, but at least it's more feasible. With the two positives next to each other.
It's bad.
And that's bad.
Okay.
So that's why.
All right. All right. Thank you so much.
Yeah. Be careful of the siren call of resonance. Like it calls to us and speaks to us and wants us to do it all the time. And I definitely put that in there to fuck with you. That is definitely what that question is meant to do. So you fell for my trap. But that's why it's on the assignment. Sorry, I need to add more slides. Okay, so Alyssa said, will I be referring to regioselectivity, stereoselectivity, regiospecificity, and stereospecificity on the exam? I will not be explicitly using those terms because, as you note, I don't ask questions like, define this term. It's just not how I think is a useful way to ask questions on an exam. Especially not a take-home exam, but even an in-person one is just, well, this isn't a take-home exam, but it's open book. But even an in-person normal closed book exam that just says memorize all these words, and it just bugs me. But will we be talking about those concepts? Yes. So what do they mean? What it's the difference between selective and specific. So just really briefly. Let's say I had this. Okay. Let's make it even smaller. Let's just make it really clear what's going on. Alyssa, what kind of reaction do you think I'm doing?
You are doing a, I want to say, E2, maybe not.
Basic, or acidic, or neutral?
You are basic.
Am I basic? Sorry, I put you on the spot here. Okay, maybe I'm being a little unfair. Neutral to acidic. I've got a tertiary leaving group. I'm definitely not doing an SN2. I'm neutral to acidic, so I'm favoring E1, SN1. It's a nice stable carbocation. E1, SN1 is looking good. I've got a small nucleophile base. I like the SN1 a little bit, so I'm doing an SN1. I'm going to say that the major product from this reaction is this. And it's the methanol opposite the isopropyl. Because the isopropyl is going to give steric bulk, it's going to block the top face, the methanol is going to come in from the bottom. Major. But I am going to get a bit of this because my intermediate is a carbocation, right? It's flat. I can attack either the top or the bottom. This reaction is stereoselective. It is favoring one stereochemical outcome because of the conditions of the reaction, but the other stereochemical outcome is not impossible. A stereospecific reaction, the other stereochemical outcome is impossible. So if I have this, and I treat that with sodium cyanide, this is an SN2. SN2s proceed via inversion of configuration.
So you said it was stereoselective?
Yeah.
The first one?
Selective. So it is, there are reasons to prefer one over the other, but the mechanism does not forbid the other outcome. We don't forbid the methanol coming in from the top. We can say, look, the top base is blocked by the isopropyl, so we prefer the methanol coming in from the bottom. It's much more likely. But we're not forbidding it coming in from the top. In the second mechanism I've drawn down there is an SN2. In the SN2, the nucleophile must come in opposite the electrophile, the leaving group. It is only possible to get that product. This one is not possible. It is not allowed. It's forbidden. You can't do it. The only way we would do it is if the nucleophile came in right where the leaving group is, but they can't because there's a leaving group there and it's blocking it. You can't pass two atoms through each other. So the bottom one is stereospecific. There is no other option. The other option is not permitted. The mechanism does not allow you to do the other thing.
Okay, that makes complete sense.
Yeah.
I don't really.
The tricky concepts. I completely agree.
I don't understand what regioselectivity versus specificity is. They explained it in the textbook, but I did not understand it whatsoever.
Same concept in that a regioselective reaction. Say I have a different one like this. I treat this with acid and water. I would expect the major product to be the Markovnikov addition. But is the secondary carbocation impossible?
Yeah. That's the anti.
Right, but is it impossible? The tertiary carbocation is more likely, but is the secondary impossible?
Is it impossible? No.
Right, so this is selective.
Okay. So what does regio mean? What does regio mean?
Means, so stereo is the stereo like RS on a carbon. Regio is which carbon are you attacking?
Okay.
So this one is attacking this carbon versus that carbon. So this is regio selective.
Okay, got it. Sorry.
Yeah, so it's geography versus arrangements in space. Yeah.
Okay.
Cool. Okay.
Thank you.
I don't see any hands up. Megan asked a question, but quickly, because Megan's already asked a question, if Christian or Dea have a question, or they're just hanging.
I have a question, Dr. Trey.
Melitza's got a question. Oh yeah, sorry, Melitza, you haven't asked any yet? Okay, good.
Yeah, I have a lot of questions, so I don't know how much time you have.
Well, you know what? We spill over. I've got some time.
Okay. Because I know you usually have a class. I know once you have to go to class.
Sometimes, but today I don't need to. I avoided booking stuff. I'm just making sure I've done that. It's just normally I have some stupid thing that I'd rather get out of after this. I prefer this.
Okay.
Okay. Yeah, no, I have nothing booked. I'm good. Go over.
Okay. Okay, so I'm just gonna share my screen.
Yeah, Christian, we can definitely do that. You can, yeah. Just while Melitza's sorting this out, actually, Christian, do you want to run your thing by me?
Yeah, sure. Can you hear me okay?
Yep.
Okay, so I was thinking of sort of making like a video that kind of feels like a nature documentary,
Go nuts.
and I actually found like a virtual voice emulator thing where it's like a text to speech and it sounds like David Attenborough.
Yeah, okay, that fits. It's directly in line with what we're looking for.
Okay, awesome.
Everything's directly in line. Yeah.
The only issue is it uses AI and the AI is not perfect, so he sounds a little drunk. Is that okay if
That's
I
even
put like
funnier.
captions?
That's even funnier.
Okay, awesome.
I'm good with that. A drunk David Attenborough talking about chemistry. That's awesome. Yeah, no, go nuts.
Okay, thanks.
It's actually kind of brilliant. Yeah. Okay, go on, Melissa.
Okay. So I was these are like my notes, so I'll just go through the questions that I had. For this question, I'm wondering why is it 1-to-1 if the
I can't quite hear you.
let's see.
You're very quiet.
Can you hear
I
me
saw
now?
you scream. You scream into your microphone?
My microphone's over here. Can you hear me now?
That's better.
Okay. I'm gonna reshare my screen then. Okay. Okay. So for this question,
Yeah.
I was wondering why is the ratio 1-to-1 if we have like this thing here sticking out?
You know what? You're right. It probably isn't exactly 1-to-1. It probably it's far enough away that I would expect the difference to be pretty minimal.
Mm-hmm.
It's small enough. But if you told me, hey, there's a higher chance of it coming from the bottom, I'd give you marks for that and go, yeah, you're absolutely right.
Okay. And then
It's just it's far enough away that I'll accept 1-to-1 as well. So
okay. And then in this example, we drew the iodine like out of the page, like towards us. Is this like favored or is it?
No.
Do you just pick one?
I just pick one. I always like drawing things out of the page.
Mm-hmm.
So if I have a choice, I will always draw out of the page first. It's just my own personal bias. There is no preference.
Okay, so for like these 3-membered rings, like we can say that it's a certain type of stereochemistry, and like we won't get docked marks for not making it like racemic.
Yeah, the only time I will do that is if I say if the reaction, I might state in a question, if the reaction is expected to produce a racemate, please draw both enantiomers.
Okay.
That will be I will explicitly say it. Otherwise, it's fine because otherwise you just end up drawing more stuff, and what's the point? I'm wasting time. Yeah.
Okay. Yeah, because I think that's what I was confused with here as well.
Yeah, no, it's absolutely fine to do.
Okay. In this question, if we had that double bond attack the hydrogen, I'm just trying to see, would the original molecule then act as another nucleophile?
Yeah. It definitely could. There's nothing else there, right?
Yeah.
I think I might be asking which carbocation you might be making is maybe where I was going with that question. But yeah, it could definitely act as another nucleophile. You'll just keep it'll basically be polymerizing.
Okay.
Yeah.
Okay, that's my Kolnikov. And then let's check this one. Okay, just trying to orient myself. This was 2 days ago and I don't remember it.
You look like you're in good shape. I'm going to say that.
Oh, I went to bed yesterday at 3 a.m. after doing 12 hours of making substitution and elimination notes.
Okay.
So
Well,
little
12
bit
hours of
sleep.
substitution elimination note sounds about right.
And that's just the note, not the practice. But
Yeah.
now I made sense out of nonsense, so that's
Great.
a good thing. Okay. Don't know what I was asking with that, so we're just gonna skip it.
How do we indicate
Um,
racemic? Is that your question? It's arbitrary which side you go from, up or down. So if you want to indicate racemic, you actually have to draw in both.
Okay.
You have a little note there.
Makes sense.
There's no way around it. You have to draw in both. Which is why sometimes I might sort of get around it, like I do in that lower questionnaire where I stick something on the adjacent carbon to say, hey, look, hint, hint, the top end is blocked. Please attack from the bottom. Which is good.
Okay. And then I was wondering, when we were doing like opening epoxides in acidic conditions, how would it work? Like, what would attack what in this case? Would we have, like, how would we open this epoxide in acidic conditions? I don't know what attacks, like, what.
So yeah, so you protonate the epoxide. So H plus goes on to the oxygen on the epoxide, which makes it positively charged. So you now have now it acts a lot like a bromonium or an iodonium. It actually reacts identical to a bromonium or an iodonium. And it's exactly the same way that a bromine would react there or an iodine. So it's so it's kind of in fast equilibrium between breaking either the oxygen carbon bonds, and you're going to have much more of the positive charge at the tertiary center.
Okay.
So the nucleophile is going to come in and attack the tertiary carbon, and you're going to get the product you drew. So as it does that, the epoxide, which this looks suspiciously like an SN2 on a tertiary center, which doesn't happen, right? But it's because the epoxide is kind of blocking the bottom face, and you might actually have a carbocation at that tertiary. You have something between a carbocation and a bond. And the nucleophile is coming in opposite the epoxide, but it's attacking that tertiary center. Like
Okay, so we create this upon protonating it, right?
Yeah.
And then do we have water attack?
Yes.
Okay.
Because that's the only nucleophile.
Okay, so then this attacks, we're opening the epoxide to the more hindered. So we're gonna get this right here.
No, that's the less
like
hindered.
that. Less hindered?
That's the less hindered site.
But doesn't won't that then open the epoxide this way?
It will, but a basic nucleophile attacks the less hindered site. Under acidic conditions, what's important isn't so much that the hindrance of the site, it's where the positive charge is localized. And so if we think about that, you have that positive charge on the oxygen, but it's also on both of the carbons.
Yeah.
And where is the positive charge more likely to be, on the secondary carbon or the tertiary carbon?
This one.
Right. So that's where the nucleophile attacks, because that's where the positive charge is.
Okay. Oh, okay. I think I got confused.
Good morning.
Good morning.
Today, awesome.
I got lots of garbage.
That's good.
Sorry, guys. Yeah. Okay. Yeah. So you attack So you attack the more hindered site because it's more positive.
Okay. So what I did here, is this wrong?
No, that's fine. I accept that.
Oh.
That's fine. It's just you need to have that O positive. So you drew a question mark over the arrow from the oxygen to the H. Before I would draw that arrow, I would have drawn the OH plus. Like I would have drawn those arrows you drew in blue on the structure you just drew, the one underneath the arrow, where you protonated the epoxide.
Okay. So this has to happen first.
Yes, because otherwise nothing happens. Because you can stir epoxides with water. Like again, if there's H plus, do something with it first. It needs to be involved in the first step of your mechanism.
Okay.
Because otherwise you have like neutral things attacking each other when there's a charge around, and that just isn't a thing that happens. Like if there's a charge around, involve the charge.
Okay, perfect. I'm gonna just add the arrow in, so then this thing opens like that. Okay, and then we'd probably create something like that. Okay. Makes sense. What did I want to ask in this one? Never mind. I think this one makes sense. It attack the more stable carbocation.
Exactly.
Yep. Okay. Perfect. This one. Okay, so realize that this is true because I asked it. Okay, and then I was wondering for if you have a carbocation with resonance that is not the owl, it cannot be SN2, right? Because it does any carbocation with resonance trump the tertiary, I guess, stability?
So if you have a carbocation that can form with resonance, it's going to be SN1 or E1 is what you're saying?
So if we have a carbocation that can, like when we're doing like the verses, or not the verses, when we're looking at substitution and eliminations, where we're comparing whether it's like primary, secondary, tertiary, leaving group.
Yeah.
Do we, if it's like primary, secondary, tertiary, but it can form resonance, and it's not the two structures that you mentioned.
Yeah, little one. Yep.
Yep. So if it can form resonance, does this mean that it cannot do SN2?
As long as it's under neutral or acidic conditions. If it's under basic conditions, you're not going to make carbocations under basic conditions.
Yeah, so if it's basic, then that would just have to, then it's E2.
It's E2. It could, a leaving group can do SN2 under, like cyanide, for example, will normally do an SN2 even if the leaving group would be in conjugation with double bond. Because cyanide is just such a shitty base. So I'm not going to, I'd say your instincts are right. I'm saying that there are exceptions.
Okay. So is that, what's the reasoning? Because when I was thinking about it, I was looking at it, the resonance is more stable than even tertiary. And
absolutely,
with a tertiary, you can't have SN2.
Right, with a tertiary you can have SN2, but you can't have SN2 with the tertiary because of the steric hindrance.
Oh, like so it's not just the stability? No, it's not about stability.
It's actually nothing to do with the stability. It's just you can't physically get a nucleophile in to the backside of of a tertiary leaving group because you've got you're going to have 3 carbons sticking your way, right? You just can't navigate that gap.
Okay.
You've been building Spartan models and things, right? So you've been seeing these space filling models.
Mm-hmm.
And I don't know if you've built any space filling models like tertiary centers. It's just you can't actually see the central carbon. It's masked by shit. Like there's just stuff all around it. You can't actually even see it. So there's no way to get a nucleophile in there.
Okay.
Sorry, yeah. The SN2 thing with the tertiary is not about stability. It's about sterics.
Okay.
Yeah. Good question. Very good question.
Okay. Okay. So I'm confused with when heat acts as like the be end all, or when it's just like a favoring thing, because
it's never a be all end all ever.
Okay. So yeah, because in this question we had heat, but we favored SN1. But then in another question where like you basically gave it to explain that he favors elimination, but you said that if we didn't draw the elimination product, we'd get marks off.
I'm not sure which. I'd have to see a specific question.
Yep.
In this case, there's not a lot of hindrance around the site.
This one.
Yes. Okay, so that's because you can do the substitution, but the substitution's reversible because you're under acid here. Like this isn't like a bromine. You have H plus protonating an alcohol, generating the water leaving group, right?
Yep.
Neutron. There's nothing stopping you once you get the ethanol in there as a nucleophile. There's nothing stopping H plus protonating the ethanol and creating an ethanol leaving group. So the substitution can happen, but you're always at the risk of tipping over to the elimination. Because even once you make the product of the substitution, that product can react to do an elimination in this case. Whereas in the previous case there, you weren't using strong acid, you were just using, it was a bromine leaving group or a halogen leaving group with an alcohol. So once the alcohol is attached, you're not really at risk of the, you don't have like tons of acid present. You're not really at risk of the, of reprotonating it and having it eliminate.
Because we don't have any hydrogens
plus.
to go back like this.
Yeah, you don't have a ton of H plus to go back. In the next example is like you're adding lots and lots of acid.
Okay. So in the previous example, essentially what you're saying is that we might say like, oh, it's substitution, we get here, but then once we get here, basically because we have acid, we can go back to here.
Right, and then if you do the elimination, the two double bonds are in resonance of each other. So they're especially good double bonds. If you didn't have that other double bond, if you didn't actually have that resonance thing going on, I don't think it would necessarily drive to elimination. I think it would be kind of, you get a mix. But eventually this will go.
Does resonance favor elimination? Is that
yeah,
another
now you
rule?
double bond, because already eliminations and substitutions are in a fine balance, right? Under the best of cases. And now what you've suddenly done is you stabilize your double bond, because now your double bond can resonate. And double bonds in resonance are more stable than double bonds that are not in resonance. And so you're already a double bond, a substitution versus elimination in an isolated system with no resonance is a pretty knife-edged case. But now suddenly you just made your double bond more stable. So now you're.
Oh, okay. I didn't know that.
I think I mentioned in lectures, but I don't think I talked about it much this year.
Okay, I'm just going to then.
That's a very specific case, and I think again I would ask, I would sort of, you would get a lot of marks for doing the other thing.
Okay.
I'm not going to have to work very hard to keep a reasonable average here because there's going to be a lot of people drawing completely ridiculous things. So, you can do well in this course by trying. Anyone who's here in this office hour is obviously trying. And to be honest, anyone who's going to watch this on YouTube later is going to be trying.
Okay. And then
this
one. If we had this here, so basically we're dealing with substitution.
Yeah.
Would it be impossible to know which one? Because we have a tertiary and then a primary, or actually, wait, which one's better? Iodine is a better leaving group. So this one, it would be SN1, right?
Right, but are we under SN1 conditions? Are we basic or are we neutral or acidic?
We're basic.
Right, so we're favoring SN2s. Like the reactivity of the nucleophile is what's going to drive it, right? And our nucleophile is very reactive. And so, yeah, so we can't do an SN2 at the tertiary. So although the iodide's a better leaving group, it doesn't matter. It's impossible to get to.
Okay.
And then in the next example there, you can't do any SN2s.
No.
So then the SN1 happens eventually because SN2 is impossible. But it's only because there's no SN2 possible.
Okay.
And it's because cyanide is a shitty base, so it doesn't do E2s. So like it doesn't do the E2s, it can't do the SN2. So even though you're under conditions that would favor E2 and SN2, neither of those is really possible. So you're left with doing SN1.
Okay, so the cyanide ion would favor, like it automatically like says like it's not elimination, it can be substitution, but because it's charged, it is favoring the SN2.
Absolutely.
Okay. 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 That's what I had from there. And then I just wanna I have two questions just I'm gonna ask with my mic. It's regarding like back 3 months ago. Now that we've added hyperconjugation, is the order of stability going to be octet resonance or octet atom, sometimes resonance trumps, but then resonance, and then what is hybridization? There we go. And then hyperconjugation, and then induction.
Yeah, hyperconjugation and induction can sometimes flip, right? So if the
Yeah,
induction
yeah.
is really
There's
strong
those
immediately,
like if it's like directly attached to the
right?
carbon.
But you're right. So it's hyperconjugation, then induction with an asterisk.
Yes.
Yes.
Yeah.
Absolutely.
Okay. Okay. And then my second question was regarding carbonyl chemistry. I'm wondering how many marks are we gonna lose if we like completely just don't know how to draw the arrows? Like if it's reversible or not.
Like if the equilibrium arrows, you mean?
Like when we're drawing out mechanisms, I'm not paying attention to like if my arrow is going to be double-sided or if it's just going to be one way.
You're not going to lose any marks.
Okay.
I think you need to recognize what might be in equilibrium with deciding how the mechanism goes, but I'm not asking you to make sure you draw equilibrium arrows. I'm fine, because normally we're sort of thinking, hey, how do I get to the product? And so I'm fine if you just draw them forward. I'm drawing equilibrium arrows to explain reactivity and why things do the things they do, but it is perfectly fine for you not to draw them at this point. I'm okay with that.
Okay, perfect. Thank you so much.
You're welcome. Well, that was 20 minutes of rapid fire stuff. So I guess it would be really, really mean of me to say no one else I can ask any questions. So actually, Megan, I can do 1B. Do you still want that one?
Yes, if that's okay.
Yeah, that's fine. I think I might wrap it up there. After, oops, wrong screen.
Could you potentially do another office hour this week? Like maybe on Friday or something like that?
You know what? As we're getting more of them, getting closer to the exam, yeah, I'll do that. I'll post it. I'll post an announcement. Yeah. Yeah, I'll need to find a time. Might be right after class on Friday, actually. Like the labs are over now, right?
Yeah.
Oh, thank God. Okay. Yeah.
Yep, I was about to say thank God.
Anyway. We have done a half-decent job of adapting the labs to a pandemic situation with half the class remote and half of it in person, and it still sucks. I have very, very strong opinions about the labs being a bit too much busy work on things, and I don't like it. Because I remember spending all my time in second year writing lab reports, like literally all my time, because I had 4 of them a week. And we had 12 labs per course, so I had 48 labs in the first semester of second year, and it was hell. Like it was just, that's all I did was write lab reports, and so much of it just felt like busy work. Okay. Anyways, I'm now bitching. So what I'm going to do is I'm going to take the benzoyl peroxide. That gives you a clue this is going to be a radical reaction. So this actually ties in with what we're doing now in class. And at the time, it was for the assignment when I posted this, I had just said in class, hey, you get the anti-Markovnikov product if you do this, which isn't quite true with this one. So let's think about what goes on here. And it's because radicals are weird, and I've corrected in the marking scheme. So if you have benzoyl peroxide, and you add some heat, we saw this, I think, on Friday. Maybe it was yesterday. I don't know anymore. Anyways, you get 2 phenyl radicals. Those then look for the weakest bond available. The weakest bond available is the HBr bond. To make benzene and a bromine radical. The bromine radical looks for the weakest bond available, which is the HBr bond, but that's non-productive, so I'm going to skip it. So it looks for the second weakest bond, which is the carbon-carbon double bond. Now, this is where I had a mistake in the marking scheme until I think last year, and it sat there for 4 years. So we're going to make the most stable radical. So we have a choice of radical. Our choices, so actually this is a really good question if Guntas is still here. So we have a choice of radicals. Anyone guess which one's more stable? So with the carbocation, we were saying it was really bad resonance having a carbocation here, but radicals don't behave the same way. Because if I draw the resonance structure of that, it's not like I have a carbocation and I have all this induction problems. I now just have, you know, a perfectly acceptable neutral oxygen. It's a radical, it's not happy, but it's not positively charged. Yeah, it doesn't have its full octet. But it's not like it doesn't have its full octet, it's positively charged. It doesn't have its full octet, it's neutral. So this is actually a perfectly reasonable resonance. And there's no resonance here. So this is the more stable radical. Now, given a choice, I can actually use either of them for the next reaction. We haven't talked about enol chemistry, which is actually this whole oxygen-carbon double bond moving around thing, and we're not going to. So I'm going to actually use the carbon, but it will be okay if somebody used the oxygen. I would give them the marks. So this thing here, you can't see my circling of the line, can then react with an HBr radical because it's the most weakest bond. Generate the bromine radical, and our product of this reaction is going to be that. So in this case, we have this radical condition, which normally gives you the anti-Markovnikov addition. But in this case, because the way the resonance works, this anti-Markovnikov addition, because there's no carbocation formed, it's anti-Markovnikov, but it gives you the same product as the Markovnikov, because those aren't products, those are mechanisms. A Markovnikov addition is one that involves a carbocation. Anti-Markovnikov addition does not involve a carbocation. In this case, though, just because of the resonance stabilization of the radical, you get the same product. regardless of whether you do this using HBR straight up or HBR and this radical initiator. Okay. Yeah, Christian, if you want to send those in an email, I think that might be better. If you, especially if you want to, if you have a question about, I'll have an extra office hour if you have just a general question. If you have a question about the marking, please send in an email using that form. It just allows me to keep track of everything, and I'm overwhelmed by emails, and so I'm less likely to lose this. And the other thing is it does make people think a little bit more. So sometimes you'll go, oh, no, I understand why I got that wrong when they do it, which is kind of the point. So it makes my life a little easier. Okay. I love you all, but I am sick of standing here in office hours right now. And we've gone half an hour over, so I'm calling it. I will just upload this, and I will talk to you later.
Thank you.
Madison, no, there isn't. I would say that there are no questions, no mechanisms that are going to be asked that are not in one of the posted assignments I posted, like my practice assignments. You're not going to see anything on the final that is not in there. Like the question will be different, but there's not going to be any mechanism that's not in there. So I think I'd be a bit more sympathetic if this was like a closed book evaluation, but keeping track of this kind of thing, because you can make any notes you like, I think is part of the exercise. And I think there's a real value in doing that and going through and just making sure. Yeah. This is one of those, I'm doing it for your own good, even though you don't believe me. And I know you don't believe me, and that's okay. Yeah, so Dea, if you can do all the assignments and you understand, like, so the caution I'm going to say is yes. Let's say you went through the assignments blind, you got all the questions right. Yeah, you are in really good shape because the assignments are harder than the exam. They are. I can ask you harder questions on the assignments because they're not for marks, and then I can teach you something by going through the question, like through the people going through the response key and going, oh, I see. The assignments are to learn shit. The examination is so that I can evaluate the students, and the students who've learned more shit end up with a higher mark than students who've learned less shit. And still get a mark distribution that is acceptable to the University of Windsor. There's this whole movement towards ungrading right now, where the idea is that we move courses towards pass-fail and we stop issuing grades, because try and recapture the idea of learning for the sake of learning. And I love the concept. I love the idea. I also know that the competition of grades is valuable and is motivating, and med schools want grades. So as cool as the idea is of switching to a pass-fail system is, it's not. Yeah, I don't know. Exactly, right? Well, to be honest, master's programs do. If I'm looking for students for my research group, I don't even really look at the GPA. It's like, did you get your degree? So did you do over 50%? And at that point, then I'm looking to see, okay, so what have you done? Do you have any research experience or stuff? I don't give a shit about grades. Grades do not translate well into ability to do things. Anyways. Okay. Yeah, hey, I get to make my own rules because it's wonderful being a research professor.
I like your rules.
They work well. I get good students. Okay, well, take care, guys. Have a really good rest of your day, and I will see you all tomorrow. Bye.